Welcome to the deep dive. We're here to sift through complex information and pull out the key insights for you.
Glad to be here.
Today, we're diving into Kubernetes Best Practices, second edition. It's written by some heavy hitters: Brendan Burns, Eddie Villalba, Dave Strebel, and Lachlan Evenson.
That's right.
Our goal, basically, to take their years of experience and boil it down so you can build better apps faster, with more confidence using Kubernetes.
Yeah, exactly. This book isn't really a Kubernetes 101. It kind of assumes, the basics.
Right.
It's more about managing container orchestration effectively when things get real at scale. It's packed with patterns, practices, stuff the authors learned the hard way, helping people out.
Okay, so let's start with a core idea. Kubernetes uses a declarative approach. What does that actually mean for how we manage things compared to, say, scripting everything imperatively?
Well, it's a pretty big shift, actually. The key thing they stress is that your declarative files, usually YAML, maybe JSON, become the single source of truth.
The source of truth, okay.
Yeah. So instead of writing scripts saying how to deploy step by step, you just define the what, the desired end state.
Ah, I see.
And Kubernetes figures out how to get there. It's way easier to understand, to replicate, to version control. They strongly recommend using standard software engineering practices on these files.
Like version control, code reviews.
Exactly. Version control, code review, applied directly to your infrastructure configuration. Imagine reliably recreating a complex setup just by applying files from Git. That's the power.
That does sound powerful. But how should we actually organize all these files? I imagine it could get messy.
It definitely could. So they recommend a structure. Think of an application service, maybe what a small team of like 8 to 12 people works on.
Okay.
Give that its own directory. Then inside that, have subdirectories for the different parts. Front end, Redis, file server, that kind of thing. Keeps it manageable.
Got it. And then deploying the actual apps, what's the go-to resource?
For most typical services, you'll want to use deployment resources.
Deployments.
Yeah. They're the workhorses. They manage replica sets underneath, which handle creating identical copies replicas for redundancy and scaling.
Right, redundancy and scale.
And deployments add versioning and rollout strategies on top. So your front-end app might have replicas. 2, in its deployment spec, maybe define specific CPU and memory resources like CPU 1.0, memory 1G.
Okay. And the container images themselves. You mentioned versioning.
Yeah.
What's the best practice there, especially for production?
Oh, this is critical. And a surprisingly common mistake. Never, ever use the latest tag in production.
Never use latest. Why not?
Because it's mutable. It can change unexpectedly. It's like trying to guarantee a specific outcome when one of your key ingredients keeps changing its properties.
Ah, right. Unpredictable.
Exactly. So treat your image tags as immutable. Use a combination like semantic versioning plus the git SHA hash. Something like v1.1.1 bfeta01f.
Okay, specific and unchanging.
Yeah. It makes deployments truly reproducible, helps track down issues, and it's a big step in mitigating supply chain attacks, too, because you know exactly what code is running.
Makes sense. Now, configuration. The book talks about ConfigMaps and secrets. Why separate them, and is there anything tricky about secrets?
Good question. So both are about decoupling configuration from your application image, which is great. ConfigMaps are for your non-sensitive stuff, key value pairs, maybe JSON or XML config files.
Regular config.
Right. Secrets are, well, for secrets, passwords, API keys, certs. But here's the crucial bit, the nuance that trips people up.
Uh-oh.
By default, Kubernetes secrets are just base64 encoded. They are not encrypted at rest, and etc.
Wait, really? Not encrypted?
Not by default, no. Base64 is just encoding, not encryption. Anyone with access to etc. backups or etc. itself can easily decode them.
Wow, okay. That's important. So how do you secure them properly?
You absolutely need to configure an encryption provider with the Kubernetes API server, or use a key management system, a KMS.
Right. Use proper encryption tools.
Or another approach for runtime security is mounting secrets using a tmsif volume. That's rammed back, so the secret data only lives in the pod's memory, never hits the disk. Much harder to compromise.
It's interesting. And they mentioned something about how missing keys are handled.
Yeah, quick point. If you reference a specific key using ConfigMap keyref or secret keyref and it's missing, the pod won't start, which is usually good. But if you use and-from to load all keys, it'll just skip any invalid ones. So different behaviors to be aware of.
Okay, good to know. So our app is running, configured. How do we let the outside world talk to it?
Right, exposure.
Yeah.
Typically, you'll use a Kubernetes service resource. that provides internal load balancing for TCP or UDP traffic across your pods.
A service, okay.
But for HTTP or HTTPS traffic, especially from outside the cluster, you usually combine that service with an Ingress resource.
Ingress, what does that add?
Ingress gives you smarter Layer 7 load balancing. Think path-based routing, host-based routing. So you can send requests for AppEP to your backend service and requests to, say, a static file service.
Ah, intelligent routing.
Exactly. And one small detail, the order of the rules in your Ingress definition actually matters for how requests get matched. Something to keep in mind.
Right. Okay, so that covers basic deployment. But what about state? Managing data reliably. That's always the hard part in distributed systems, isn't it?
It really is.
Ooh.
And Kubernetes doesn't magically solve it. The book's advice is pretty clear.
All right.
If you can use a managed stateful service, like a database as a service from your cloud provider, do it.
Use sauce if possible.
Yeah. Because running stateful things yourself, dealing with backups, data locality, failover, redundancy, it's complex. Very complex.
But sometimes you have to run it yourself, right?
Those times you do. And for those cases, Kubernetes provides StatefulSets.
StatefulSets, how are they different from deployment?
They offer stronger guarantees. Unlike deployments where pods are interchangeable, StatefulSet pods get stable, unique network identifiers, and persistent storage that follows them.
Stable identities.
Exactly.
Yeah.
And they have a predictable, ordered scaling and update process. Crucial for things like cluster databases, message queues, like Redis, where node identity and order matters. They use persistent volume claims to get their dedicated storage.
Okay, StatefulSets for when you really need stable state in the cluster. Now, let's get into CI/CD. Continuous integration, continuous delivery. This feels essential for Kubernetes. What's the core philosophy here?
Absolutely essential. The goal is, ideally, a fully automated pipeline. Code gets checked in, tests run, and it rolls out to production without error-prone manual steps.
Total automation.
That's the dream.
Yeah.
And a key part of this, they emphasize, is keeping both your application code and your Kubernetes configuration. Your manifest, your Helm charts, together in version control, usually Git.
Ah, config Git too.
Yes. It embraces DevOps principles. Your infrastructure is code. I remember this one team spent days debugging a prod fire. Turned out someone had manually tweaked a config file on one server. Total chaos. GitOps prevents that.
Right, avoids that drift. So for the actual deployment part of CI/CD, what strategies does Kubernetes offer?
Well, the built-in default for deployments is a rolling update.
Rolling update.
Yeah. Kubernetes replaces old pods with new ones gradually, ensuring zero downtime if done right. You can tweak how it works with settings like max unavailable, how many can be down, and max surge, how many extra can be created.
So you have some control.
You do, but for more sophisticated strategies, you often look beyond the basic deployment controller. There's blue-green deployment.
Oh, green.
Where you have two identical environments, blue and green. You deploy the new version to the inactive one, test it, then flip the traffic over instantly.
Okay, instant switch.
And then there's canary deployment. You release the new version to a small subset of users. First, the canaries.
Test the waters.
Exactly. You monitor carefully, and if it all looks good, you gradually roll it out to everyone else. These often rely on smarter traffic shifting, maybe using an Ingress controller feature or a service mesh like Istio.
Right, service mesh comes into play there. Okay, what about deploying globally across multiple regions? That adds complexity.
For sure. First step is getting your container images close to users. Use your cloud provider's geo-replication features for container registries. That's table stakes.
Get the images distributed.
Then, managing the configuration differences between regions or environments. Staging versus prod, US versus EU. That's where parameterization is key. Tools like Helm are designed for this.
Helm for templating.
Yeah. It lets you define a base configuration and then provide environment-specific values files. Way better than copying and pasting YAML files and hoping you change the right lines. That just leads to configuration drift.
Avoid copy-paste errors.
Absolutely. And before you even think about rolling out globally, you need solid pre-rollout validation.
More testing.
Comprehensive testing. Full integration tests using production-like data, anonymized of course, and proper load testing. Simulate realistic traffic. Maybe even replay production logs, carefully scrubbing sensitive data.
Really hammer it before it goes live.
You have to. And even then.
Yeah.
The first real deployment of a new release. Use a canary region.
A whole region as a canary.
Yeah, a smaller designated production region. You roll out there first. Let internal teams, maybe some select large customers, use it. It's your final early warning system before hitting major regions.
Okay, a canary region. Smart. But inevitably, sometimes things do go wrong during a rollout. How do you prepare for that?
Preparation is everything. They really stress having clear, written checklists. for everything, even stuff that seems obvious.
Checklist.
And practice. Run drills. Like practice draining traffic from a region using DNS load balancing. That stuff can take time. They mentioned nearly a day for DNS to fully propagate sometimes.
Wow, a day.
Yeah. So practicing builds confidence, shakes out problems in your process or architecture. It means less panic when a real incident happens.
Practice, practice, practice. Got it. Okay, beyond deploying, how do we actually operate these systems day to day? Keeping an eye on things, monitoring.
Right. Observability is key. The book makes a clear distinction between metrics and logs.
Metrics versus logs.
Metrics are numeric, aggregatable data points. CPU usage, request latency, error rates, things you can graph and alert on easily. Logs are discrete events, usually text, good for deep debugging, but harder to aggregate. They're complementary.
So we need both.
Definitely. For monitoring strategy, they recommend 2 methods. For infrastructure, the USE method. Utilization, saturation, and errors for each resource.
USE for infrastructure.
And for your actual services, the RBAC method.
Yeah.
Rate, request per second, errors, error rate, and duration latency. This focuses more on the end-user experience.
RAD for services. Makes sense. Tools.
They highlight Prometheus for collecting metrics and Grafana for visualizing them. Pretty standard, powerful combination of the Kubernetes world.
Okay. Now, something I know plagues operations teams, alert fatigue. Just getting spammed with notifications. How do we avoid that?
Oh yeah, it's a killer for morale and effectiveness. The core advice is only alert on things that actually impact your service level objectives, SLOs, and your customer experience.
Alert on what matters.
Exactly. If an issue pops up briefly and then resolves itself without any intervention, did it really need to wake someone up at 3 a.m.? Probably not.
Good point.
So, focus alerts on sustained problems affecting users. Standardize your thresholds. Maybe an issue has to persist for 5 minutes before alerting. Ensure alerts have context, point to runbooks, and go to the right team, not just some giant email list.
Targeted, actionable alerts.
Precisely. They even reference Robbie Washuk's My Philosophy on Alerting, which is a classic read on this topic.
We'll link that. Okay, let's pivot to security, always top of mind. What's the overall approach for securing Kubernetes?
It's all about defense in depth and the principle of least privilege. Don't rely on just one security layer, and grant only the permissions absolutely necessary.
Defense in depth, least privilege. Where do you start?
Securing the control plane itself is paramount, especially etc. That's the brain, remember. It holds all the cluster state.
Right, the etc. database.
If someone gets direct access to etc., they bypass all other Kubernetes security, RBAC, admission controllers, everything. So lock it down. Strong credentials, network firewalls, only allow the API server to talk to it directly.
Protect the brain. Got it. And we talked about secrets earlier, the encryption issue.
Yes, bears repeating. Default secrets are not encrypted at rest. You must configure an encryption provider or use external tools like the Secret Store driver, which mounts secrets into pods via temporary RAM-backed file systems, or use something like HashiCorp Vault.
So multiple options for proper secret management.
Definitely. Don't rely on base64.
Okay. What about enforcing policies across the whole cluster? Like only pull images from our trusted registry.
That's where policy engines come in.
Yeah.
They highlight gatekeepers, which is based on the Open Policy Agent, or OPA.
Gatekeeper and OPA.
Yeah. You define constraints specifying what's not allowed. Like your example, disallow images not from registry X. Gatekeeper acts as an admission controller, checking resources as they're created or updated.
So it can block bad configs.
It can. You can set the enforcement action to deny, or you can set it to warn during rollout or dry run, just to see what would be blocked. It also has an audit function to check existing resources. Very powerful for governance.
Cool. And controlling who can do what within the cluster, user permissions.
That's role-based access control, or RBAC. It's the standard recommended authorization method in Kubernetes.
RBAC.
You define roles, sets of permissions on resources, and role bindings, linking users or groups to roles. It's all stored as Kubernetes objects. They specifically warn against using older methods like ABAC or webhook authorizers, especially in multi-master setups due to complexity. Stick with RBAC.
Stick with RBAC. Okay, what about securing the actual applications running in the pods down at the workload level?
Several layers there too.
Mm-hmm.
First, there's pod security admission. It's a built-in admission controller that enforces pod security standards at the cluster level, things like preventing privileged containers.
Pod security admission.
Then you get into Linux security mechanisms, like seccomp. Secure computing mode. It lets you filter the system calls a container can make. It's powerful, but often tricky to get right. However, Even applying the default seccomp profile provided by the container runtime gives a good security boost.
Filter system calls. What else?
Simple things. Run your application process as a non-root user inside the container. Huge win. Use distro or scratch-based images with just your app and its direct dependencies, nothing else. Massively reduces the attack surface.
Minimize the image.
Exactly. And finally, regularly scan your container images for vulnerabilities. Tools like Trivy or Claire can do this. You can even integrate these scans into your CI/CD pipeline or use an admission controller to block vulnerable images from being deployed.
Scan early, scan often. Okay. Now, Kubernetes itself is powerful, but sometimes you want to build things on top of it, right? Or handle really specialized tasks.
Absolutely. You can kind of wrap Kubernetes, hide its complexity behind a simpler interface, or you could actually extend Kubernetes itself.
Extend Kubernetes. How?
The main mechanism is custom resource definitions, or CRDs. They let you add your own resource types to the Kubernetes API. So maybe you want a replicated database resource that represents a primary and replicas. You define the CRD, and suddenly kubectl get replicated databases is a thing.
You create your own API objects.
Exactly. And then you typically need something to manage those custom resources. That's where operators come in.
Operators?
An operator is basically software running in your cluster that encodes the operational knowledge for a specific application. It watches your custom resources, like replicated database, and takes actions, creates deployments, services, handles backups, upgrades based on the spec, makes complex stateful apps run like native Kubernetes services.
So operators automate complex app management.
Precisely. Think databases, message queues, monitoring systems. OperatorHub.io is a good place to find existing ones.
Cool. And speaking of specialized workloads, machine learning seems huge on Kubernetes now. Why is it such a good fit?
Several reasons. One, Kubernetes just everywhere. Developers know it. Two, scalability. ML training, especially with GPUs, needs massive elastic scaling, which Kubernetes handles well with auto-scaling.
Scalability for GPUs.
Right. Three, extensibility. Kubernetes has device plugins that let you expose specialized hardware, like GPUs, FPGAs, or InfiniBand adapters to containers in a standard way.
Handle special hardware.
Plus, it supports the whole workflow. You can run Jupyter notebooks for development, use the job resource type for batch training tasks, and then deploy models for serving. And the key thing for efficiency, make the GPU the bottleneck.
GPU is the bottleneck. Why?
Because GPUs are expensive. You want to make sure you're keeping them busy, feeding them data fast enough. So you need to monitor GPU utilization, yes, but also CPU, network, and storage I/O to find and eliminate other bottlenecks.
Optimize the whole pipeline for the expensive part. Makes sense. Okay, what about managing multiple clusters? When does that become necessary?
Good question. Kubernetes provides what's called soft multi-tenancy using namespaces. Different teams can work in the same cluster, isolated by namespaces and RBAC.
Soft multi-tenancy.
But sometimes you need hard multi-tenancy, maybe for strict regulatory compliance or to limit the blast radius if something goes very wrong, or for geographic distribution. That often leads to running multiple clusters.
Hard multi-tenancy means multiple clusters.
Often, yes. But it definitely adds operational overhead. Managing one cluster is work, managing 10 is more work. So automation becomes absolutely critical. Think infrastructure as code tools like Terraform or Pulumi to provision and manage the clusters themselves.
Automate cluster management.
You have to, really.
And I keep hearing GitOps in this multi-cluster context. What is a GitOps and why is it helpful here?
GitOps is a specific workflow, an operational model. The core idea is that your Git repository is the single source of truth for the desired state of your infrastructure and applications.
Git is the truth again?
Yes. And you have an agent, tools like Flux or Argo CD running in your cluster, or managing multiple clusters, that constantly compares the live state to what's in Git.
It watches Git and applies changes.
Exactly. It automatically pulls changes from Git and applies them to the cluster. Or, maybe more accurately, it ensures the cluster converges to the state defined in Git.
Continuous reconciliation.
Right. It gives you version history for your cluster state, easy rollbacks via Git revert, an audit trail, and it helps drastically reduce configuration drift, especially across multiple clusters managed from the same repo structure. It enhances security too, as changes happen via Git commits and reviews, not direct kubectl apply commands.
That sounds very powerful. What about secrets in GitOps? Putting secrets in Git feels wrong.
It is wrong to put plain text secrets in Git. That's where tools like sealed secrets come in.
Sealed secret?
Yeah. You encrypt your Kubernetes secret object before committing it to Git, using a public key associated with a controller running in your target cluster. Only that controller with its private key can decrypt the sealed secret back into a regular secret inside the cluster.
Ah, so it's encrypted in Git, decrypted only in the cluster.
Exactly. Safe to store in Git, usable by your applications. It's a common pattern for managing secrets in a GitOps workflow.
Very clever. Okay, shifting gears one last time. Testing. We've talked about unit tests, integration tests, load tests, but how do we really build resilience? Test for the unexpected?
This gets into areas like chaos testing. It's about deliberately injecting failures or unusual conditions into your system to see how it behaves.
Injecting failures, like
Yeah.
breaking things on purpose.
Sort of, but controlled failures. Introduce network latency between services using a tool like Toxiproxy. Randomly terminate pods. Simulate a dependency failing. The idea is to find weaknesses before a real incident does, and to verify your redundancy and recovery mechanisms actually work.
Build resilience through controlled chaos.
Exactly. But a huge prerequisite is good monitoring. You need to be able to observe the impact of the chaos you're injecting.
Makes sense. And load testing. We mentioned it for pre-rollout, but its role in resilience.
Load testing is about understanding your system's limits. How does it behave under realistic or even heavy load? Where does it start to slow down or break? Identifying those bottlenecks and capacity limits helps prevent performance regressions and ensures you can handle peak traffic.
Find the breaking points under load.
Right. Replaying production logs can be a good source of realistic traffic patterns, but again, be careful with data privacy and dependencies. The goal is understanding performance under stress.
Okay. And then there are experiments. How are they different?
Experiments are usually longer running, like A/B tests. You might expose a small percentage of users to a slightly different version of a feature or infrastructure change.
Like canary releases, but for learning.
Kind of, yeah. The main goal isn't just to test stability like a canary, but to actively learn about the impact of a change on user behavior or key business metrics. Does this change improve conversion rates? Does it reduce latency? You measure the impact on a small group first.
Learn with minimal impact.
Precisely. They recommend using separate deployments, maybe managed via a service mesh for fine-grained traffic splitting, to run these experiments robustly. It can be more complex to set up, but gives you clearer results.
Chaos, load, experiments, different tools for building robust systems. You know, it's funny, we're talking about all this complex engineering, and the cover of the book has a duck on it.
Yeah, a mallard duck.
Does it have some deep metaphorical meaning related to Kubernetes?
Well, maybe. Mallards actually have this fascinating ability called unihemispheric sleep.
Unihemispheric, one hemisphere.
Yeah, they can literally sleep with half their brain at a time,
Yes.
while the other half stays awake and alert, one eye open, watching for predators.
Whoa. That's actually kind of like a distributed system with active monitoring and fault tolerance.
Right? Nature's high availability. It's a pretty amazing adaptation for survival, especially for birds resting on open water.
That's incredible. A duck practicing continuous monitoring.
The natural world has its own best practices.
Indeed. Well, that feels like a good place to wrap up. You have just navigated a really deep dive into Kubernetes best practices.
We covered a lot of ground.
From those core deployment concepts and state management through CI/CD, global rollouts, observability, security, all the way to advanced patterns and testing for resilience. Hopefully, you've got a much clearer picture now of how to use Kubernetes more effectively.
Yeah. The hope is that distilling this kind of real-world experience helps you avoid some common bumps in the road. Building systems that are stable, reliable, secure, robust. That's the goal.
It's all about understanding and applying the knowledge, right? Thinking critically about how these practices fit your own context.
Absolutely. There's no substitute for that.
The journey in this cloud-native world, it's always evolving, kind of like figuring out how a duck sleeps with one eye open. There are always more layers to uncover. Keep exploring, keep asking questions.
Keep diving deep.
Exactly. Thanks for joining us on The Deep Dive.